Welcome back, everyone. I hope you grab a drink and you relax. Now we're gonna head to our next speaker, Arlo Belshee. I've met Arlo on the Legacy Card Rocks community that I will share in the chat in a moment. But you may already know him because he wrote famous articles on naming as a process. So if you ever came across that series of blog posts, that's a very, very good one on naming things incrementally. And today is going to talk about how to master legacy code incrementally. I don't want to spoil what it's going to talk about, but as Adriana presented before, incremental is one of the pillar of working with existing code. Although he's an expert in working with existing code, his goal is to take you and achieve concrete results in 2 days to reach to a no bug state of things. And yeah, it will tell you more about that in a moment. So, Arlo, please, you're up.
Hi, thank you very much. So yeah, I mean, I won't get you to no bugs in 2 days, but you will see results every 2 days from everything that you learn, and it'll get you to no bugs consistently. The whole point is that we don't slow down to address technical debt. In fact, addressing technical debt speeds up today's story, and it also speeds up the future. So let's look at how we get there. And to get there, let's start with makers. So way back 250 years ago, Voltaire said this quote, perfect is the enemy of the good. And makers have really adopted this philosophy. It used to be we all produced code in the feature factory, but we've really started with DevOps and lean startup movement to shift at least many companies out of the whole feature factory deadline basis. Feature factory and deadline was all about making a perfect release. We would take the time, do it right, make sure it's exactly right, wait several years to do that, and ship it. Lean Startup taught us, instead of trying to get it perfect, let's get it good enough to get data, and then get it out there, get some data, and iterate over and over and over. And so I want to celebrate that. It's far more effective. And those groups have been able to get to a better product in less time by not trying to make it perfect, just make it good. Perfection prevents making it good and getting it out there. So I really want to celebrate that. And it allows them to solve so much more. But it doesn't solve this. Groups that are doing lean startup and DevOps, still many, many, many of them create and die under more debt and more technical debt. The reason is because technical debt is a different kind of problem. It's a yarn ball. Every single part ties to every other part. If you try to untangle any one bit, you just get tangled up in something else. It feels like you're like this cat, always on the edge of hopelessness, just tied up, can't move. But on the edge, and maybe you can save it. Or is that really true? Because when I talk to a bunch of people at MenderCon, menders never feel like they're on the edge of hopeless, even when they're in the same code. And we discovered an interesting thing, which is that all of us share the same hobby. Well, we have several hobbies, but one of those that we share is untying literal yarn snarls. Many of us have wives or friends or ourselves who do various fiber crafts and knitting and so on, and there are always balls of yarn. And those people, as they're making their thing, at some point the yarn ball gets too nasty and they hand it to us, and we tidily and happily just untie it. Right? Menders find this process of unsnarling soothing. Makers find it frustrating. Why? The reason is because there isn't actually one knot. It may look like one knot in this massive snarl, but really it's 50,000 separate knots, each one tied to all the others. And menders have figured out how to solve one of the little small knots without making any new knot. So I call this, good is the enemy of slightly less terrible. Our goal is not to make anything good. In fact, good is usually so far away and so impossible we can't afford it. What we're looking for is less shitty, right? So slightly less terrible. Good fails with technical debt. We just can't afford there. We can't get there in one step. Menders set their sights lower, and by setting their sights lower, we can repair damaged code bases in place while adding feature. We can perform that miracle. So makers had exactly the right idea of go incremental and get things. We just need to take it further and stop trying to make anything good. So let's look at tech debt. Tech debt creates two fundamental business problems. We create more and more bugs over time, and we find those bugs later and later. We can't find them early. Now, it does create other issues like slowing down development a little bit and the like, but those ones, honestly, at a wider business sense, they're affordable. Products make lots and lots of money, or they make almost no money at all. And if you're making lots of money, you can afford a slight increase in costs. And if you're making no money at all, you can't afford the costs anyway, so who cares? So the result is that cost doesn't matter very much, but bugs, uncertainty, and risk, those kill products, those cost customers. So as tech debt mounts, it causes a problem for businesses by creating bugs, creating uncertainty. And the fact that we find these bugs later and later just amplifies the uncertainty. Now, underlying that business problem, there are two fundamental recurring technical problems, these knots that just happen over and over and over 50,000 times. And each one of them is usually one of the two cases, either code that is difficult and dangerous to change, or it is difficult to isolate and test. So we want to solve those two technical knots. If we can solve code that is dangerous to change and solve code that is difficult to isolate and test, then we can solve that fundamental business problem, and we can get rid of all of the defects and risk. So let's start with dangerous code. Now, first, let's look at what makes code dangerous. If we're going to address it, we need to look at it. Now, what I mean by dangerous code is that a normal, good developer who's really proficient and really practicing and being careful goes and tries to change this code and accidentally creates a bug. Right? Bugs don't happen randomly, and bugs don't happen by malicious action by developers. Bugs happen because the code and environment is so dangerous that even the most well-meaning developer screws up. And so let's look at what causes them to screw up. And there's data on this. So the data show, from looking at a whole bunch of bug databases over time, that the most common cause of bugs is illegible code. Right? You try and read it, it is illegible or misunderstanding. You come up with the wrong set of characters, the wrong beliefs about what it's going to do. And then from that mental model, you make a change. And since your mental model doesn't match what the code's actually doing, any change you make has a very high probability of making a mistake, and therefore bug. Right? There is so much code out there that takes time and effort to understand. The vast majority, I would say all, but it's, a few people don't have it. Right? Those few people don't have these kinds of bugs. So let's look at how we can solve illegible code. And this is the heart of this is that naming is a process that Nicolo mentioned earlier. So the key is we increment by focusing on names. Now, there are all sorts of design flaws in a typical system, in this gnarly mess of code. But chasing the design patterns is hard and leads us towards good. Instead, let's ignore the design wisdom for now. Let's just focus on one name at a time. We want to do something simple and small. Now, it is very simple to name a simple thing well. If I've got a function that does one behavior and it's 3 lines long, it takes me no time to name it. It is impossible to name a complex thing well. If I've got a class that has 50 methods, each one of which is 1,000 lines long and integrates to a third of the system, there is no good name I can give that class. So we want to just focus on how do we name things well. And to do that, we will have to make them simple. Right? So the process is fairly simple. We first make names factual. We try and get the wisdom and information that is there. Then we make them good. And in the process of making them good, we will have to make them make the thing that they're naming simple. That'll guide the design fixes that we need. So naming as a process is a mechanism that you can follow one step at a time without having to think about what you're going to do next that will incrementally improve one name. In this way, it's a ratchet. It defines a forward direction. Right? As you're moving along the naming as a process cycle, every step is better than the step that was there before. Right? So it's easy to ensure that you don't backslide. You can look at a name and know where it is in the process. And once you know where it is in the process, you can identify what's the next step that I do to it to make it better. Right? And that way, as we work on names, we don't have people making the name worse again. So everyone will steadily move it forward. That ratchet process is a key part of incrementalism.
Mm.
However, to make those changes, we also need one additional feature beyond the ratchet. We need to be able to make a change safely. Right? Menders are going to be doing these renames and these changing things hundreds and hundreds of times. A single name can commonly, especially if it's one of those large classes, it can commonly involve hundreds of renames and hundreds or thousands of extractions and inlinings over a course of a 6-month period. Remember, we're doing this on code that is still untestable. Right? So we've got untested code that we're going to change hundreds or thousands of times over 6 months. We need a very high degree of safety. And the tool to do that is Proofable refactorings. We need refactorings that can guarantee that we're absolutely safe as we do an extract method. Now, if we're just changing code, there's no way we can prove that level of safety. Even if we had tests, it's safe-ish, right? So we need this provable, highly disciplined way of working where we are doing exactly one known transformation. And doing that, it is now safe to execute that each change in that sequence, which then we can compose together into a sequence of just those changes, and we can fix one knot at a time without introducing an error. So together, those two things are the key to incrementalism. A ratchet that allows us to define how to go forward and prevent backsliding, and a safe incremental change that we can do hundreds or thousands of times without accumulating risk. That will allow us, with those two things, to start fixing names. And by fixing names, we have addressed the most common danger in code. Not all of it, but the most common. So let's, having fixed a lot of the bugs and reduced the number of bugs that we have, let's look at this untestability problem. Now, to look at it, we really need to start thinking about, why do we unit test? Now, we all think about it, unit test, as there to detect our mistakes. And this harkens back to that business process. We want to find bugs early. And so what could be earlier than a unit test? Well, so Corey Haim does an interesting set of experiments. He codes a lot. He does a lot of different projects as he's working with a whole bunch of different teams and on his own projects. And he's been doing all the extreme programming practices for decades, knows them. He's a master of all of it, knows this stuff. But he's continually trying to improve his abilities. And one of the things that he does do that is to look at, what is it that each practice gives me. The way he explores that is, every 6 months or a year, he'll do a project in which he will intentionally drop one practice. So he'll do all of XP except he won't pair, or all of XP except he won't do TDD, or all of XP except he will not refactor. He'll still write the test, but he won't refactor, or ... Right? And so as he does that, he discovers, what is it that I lose in this project when I drop a practice? So he did a couple of times, he's done one where he doesn't do any testing. Right? All of XP, including refactoring, but no tests at all. And you'd think he'd have a massive bug farm. What he found is he doesn't. Actually, his defect rate is almost identical to the project before. Interestingly, when he does do unit testing, his defect rate is slightly better than the project before. And most importantly, his speed is much higher. His productivity is much higher than the project before. He's able to take on new technologies. When he's not unit testing, he doesn't take on the new technologies as well. Right? So tests don't really get rid of bugs. In some way, they guide continuous improvement. And the question is, how? Let's look at what we're doing when we're testing. Now, we've got untestable code here. Untestable code is impossible to test for exactly one reason. It's because we can't get our target behavior in isolation. Right? Our target behavior is either an emergent property resulting from the interactions of several different parts of the system, or it is in one place, but that one place is intertwined with a whole bunch of other things. And either way, we can't test it because those emergent properties, in order to gather all the parts together, we have to do this massive integration test. And then there's just so many variations, so many cases that our test is a tiny percentage of the real world cases, and we don't ever really know what's going on, right? Or with it all intertwined, we end up trying to fake break it up with things like mocks, and then our test ends up not being able to verify anything that's actually true because it's all too intertwined with what's going on. So to make the code testable, I need to isolate it. Now, remember dangerous code? I said that we had addressed one of the most significant dangers, in fact, the most significant danger with illegible code. Well, the next two most significant dangers are bugs that arise from spooky action at a distance, and bugs that arise because this piece of code is just too complex and intertwined with too many other things. In other words, they arise from from code that is emergent or intertwined. Exactly the same thing that makes code difficult to test. So to make code safe, I want to isolate it. Now that's really interesting and sort of shows why unit tests don't really detect bugs. Because what the unit tests do is they act as a ratchet for code isolation. And as you isolate code better, then you prevent bugs. And the reason that Corey doesn't find that testing eliminate bugs is because his tests don't actually find or eliminate bugs. Instead, they allow him to tell when code is sufficiently isolated. Now, Corey is also an expert. He's also really good at design, just like most developers out there, which means that he also has other ways to tell when code is sufficiently isolated. You can look at code and see this stuff is intertwined. This behavior is emergent. Right? And so he naturally does the refactoring to isolate code. And in that way, he prevents bugs because he makes the code non-dangerous. However, if he's not unit testing, then the unit tests aren't showing him the unknown unknowns. His unit tests show him the ways to, show him code that is difficult to isolate that he doesn't already know how to solve. And they give him the opportunity to figure out how to solve that case. That's the way they work as a ratchet. Now, there's a big asterisk here. They only work as a ratchet if you avoid shortcuts, because the whole point is to actually isolate the code. And shortcuts, I mean integration tests. I mean the ways that most people use approval tests, where I slap it around a big chunk of code and just approve whatever's there. Right? I mean mocks, the way that most people use them. Any of these are ways to avoid changing the code under test and to wrap it around with a test. And remember, the whole point is the test is simply a ratchet to tell us how to change the code under test. If we never change the code under test, we get zero value from unit testing. Yeah, we'll be able to run these couple of tests, but as Corey found, it doesn't really find many bugs, and it doesn't change our defect rate. It'll find a lot of things that we would have found anyway, and it'll find them a little earlier. Small advantage. The big advantage comes from using it as a ratchet to really isolate code. So we want to write tests that verify isolation, that prevent us from testing anything that is an emergent behavior, that prevent us from testing anything that is intertwined with the code around us, and that require us to eliminate those emergent behaviors and collect the stuff to one place so that we test it, and that require us to eliminate that intertwined mess and snarl and isolate the one chunk so that we can verify it in isolation and know for a fact that that constitutes an identical behavior when it's intertwined with the real system. Okay? When we work with this way, it turns out running tests is actually optional. Really high-performing teams find that their unit test suite basically never fails. They are working with code that is safe and easy to change. It is not dangerous, and because the tests have already helped them isolate it, and because the code is easy to understand and already isolated, they don't make the mistake. When they don't make the mistake, the test doesn't find any mistake. And so their unit tests will run on every commit hundreds or thousands of times per day and succeed and succeed and succeed and succeed. And once a month, they'll find one mistake, right? Running the tests is actually fairly optional, doesn't provide a lot of value. Writing the tests provides the ratchet that provides the value. Great. So now we have a ratchet that will guide us isolating the code, but how do we actually perform that isolation? We need a way to copy the code and modify it to do those safe changes without introducing bugs. And the question is, how safe do we need? Now, what we need is a level that I call bug for bug compatibility. Now, I first ran into this concept when I was working at Microsoft, because Microsoft has a really strong backwards compatibility guarantee. And when I was working there, I saw a bug in a spec. I was working on OData, Open Data Initiative, and I saw a bug in the spec where it was just a little complicated and weird. Right? So I fixed it. Just simplified it, did the obvious thing. A couple weeks later, I got a call from the SQL Server team, and they said, yes, we see that bug you fixed in the spec. It is absolutely a bug. It would be better the way you do it. We need you to reintroduce that, because if you don't, we can't support it. We can't support OData without that bug in it. And we're like, asked why? This is bizarre. Right? And they said, because 2 decades ago, a large American automotive manufacturer chose to build their line of business system on top of Visual Fox Pro, which is not a Microsoft product. And Visual Fox Pro had a bug in it. And then a few years later, that manufacturer, having switched all of their factories to run using this product, lost the source code. So they have the product running. They don't need to changes. The line of business application is working just fine. It's a key element of making like a third of the cars that are produced by the US. However, they don't have the source code. And Visual Fox Pro then was running into troubles and was purchased by Microsoft and eventually incorporated into SQL Server. And so SQL Server supports running that line of business application. And ever since then, we have maintained, or Microsoft has maintained, backwards compatibility, that line of business application running in the field, even though there is no source, without recompiling, will continue to run on every updated version. And so that manufacturer can update to SQL Server 2019 and get all the security updates and everything that is necessary and still run the factory. And if we ever fix this bug, that application will fail and they will stop being able to produce cars. At which point they will stop buying our product, and they account for huge, vast amounts of revenue, right? Not just this one product, but lots of products across the company, which will come into question. So we need to maintain that bug forever. We also need that bug to not impact anybody else. And so we're very good at doing that. And we've found ways to do it. But we do need this little hole in OData that people can do it the right way, or they can do it this slightly weird way. Great. Okay. So we did that, and we maintained bug for bug compatibility. But what does that mean for us as we're trying to get dangerous code under test? Well, the problem is Microsoft really knows its customers, and they knew about this bug and ensured it. Most companies don't know their customers that well. Most companies move fast and break things, and then they just lose one customer at a time off the sides, and they don't even notice the loss. Right? They don't know the bugs that customers are depending on. And every product that's out there that's a market leader has bugs that customers are depending on. You just don't know what they are. So you need bug for bug compatibility. You need to ensure that you don't accidentally fix a bug that you don't even know exists. And tests can't provide that level of guarantee, because we can only write tests for behavior that we know exists. By definition, this is behavior we don't know exists, so it's untested. Right? And when we're making the changes, we need a way to make changes that is going to maintain these behaviors that we don't know exist. So we can't depend on the developer to look out for things. We can't depend on a test suite. What can we depend on? What we can depend on are provable refactorings. Now, provable refactorings use static analysis. they use the behavior, the definition of the language to know what transforms we can safely do. So, for example, rename that we talked about before. If I do a rename and this is the way that the one in Visual Studio works. Visual Studio IDE is continually compiling your code. Every couple of characters, it recompiles whatever changed and looks at fully through the compilation stack. Now, if I'm doing that and I perform a rename, then what I can do is I can look at the entire symbol resolution table for the entire program before the rename, and I can see every place that there is a name as basically a pointer and see what piece of code it points at. Then I can do the rename and make sure every pointer points at exactly the same thing. If it does, then I've proven without a doubt that I have just created code which will compile to exactly the same result. Right? And so that's the way that rename actually works in Visual Studio. They have some things that they do to check whether it's safe and so on, but the final check is they look at the name resolution table before, they execute the rename, they compile it, they look at the name resolution table afterwards, and they verify it's correct, and if not, they revert it. Right? That prevents any type of mistake. You can't have names escaping scopes. You can't have anything because it either changes the behavior of the application or it doesn't. Right? We need similarly safe refactorings that use static analysis for all the behaviors that we want to do. And there are some. Right? Common IDEs that really do semantic analysis, like the ones by JetBrains or Microsoft, do extract method in a safe way. They have a very small number of known won't fix bugs, so you can see whether your code is in that case, and if not, you're safe, and if so, you aren't. Right? Introduce parameter object. Each of these exist. And some of these, we're also developing refactorings. If you go look on GitHub, I have a set of provable refactoring recipes that are manual things. So C++, for example, there is no IDE or tool that does it well enough. But the C++ compiler is really, really powerful. And so we can lean on the compiler if we have the right recipe that takes us through things in the order such that every mistake we could make is something the compiler could detect. If I just rename code, the compiler can't detect the sorts of mistakes that I'll make if I just retype the name. But there is a sequence that will allow it to detect every mistake I can make along the way. The same for extract method and so on. So isolating code really depends on these three provable refactorings. Now, we don't need a large number of provable refactorings. You can see from this and from before, we can get a lot of progress with just a small number as long as they are really, really, really safe. And then we can maintain bug-to-bug compatibility. This is the full mender strategy for preventing bugs. 2 ratchets and 1 kind of chain. The ratchets always define how to go forward. We have totally safe changes, and because we have totally safe changes, we can make thousands and thousands of changes. If they weren't totally safe, then compositing thousands of changes together would increase risk over time, and eventually we'd be creating bugs. Because they're totally safe, 0 times 0 plus 0 plus 0 plus 0, we end up with no risk. Right? And then these ratchets allow us to navigate. Once we are able to break things into thousands and thousands of changes, we need to be able to define going forward because we will have many teams doing thousands of changes all at once, all across the code base. And I'm changing one thing and I get it forward a little bit and then I go change something else and then someone else comes back and changes it. And we need a way for everybody to orient and navigate forward. And that's what these ratchets do. They allow us to see which direction is forward, which direction is backward, and prevent the backsliding. So then we can split those changes across all the teams. Now that's fantastic. It solves the problem, except menders find it extraordinarily frustrating. The problem is that in order to operate that way, you need a set of skills that are not commonly taught. And you need a mindset that is commonly avoided, that is actually seen as a bad thing. Right? This strategy doesn't just require that we have some menders. It actually requires that everyone who touches the code is a mender, because everyone who touches the code either understands how to work with a ratchet and do safe changes, or they don't. And it only takes a couple of people going backwards to undo the work of hundreds of people going forwards. Usually, menders are outnumbered rather than outnumbering the makers. Right? So what we need is some way to fill in those skills and mindset. We need some way to create menders, because even if we have the technical solution, does it matter if no one can pull it off? So let's look at how we make menders. So the mender mindset is something that I call code by refactoring. Right? That mindset is that we don't actually create. We don't code. Makers create. They think of what they want. They think of how they want it to come into existence, and they go make it. Menders never do this. Instead, they discover and nurture. They think of what the code does, and they think of how they would like the code to be. And then they discover the parts of code that are close to that, and they pull them and they tease them and they nurture. It's like a bonsai tree, right? You don't just create the bonsai tree. You have a tree, and you can't make anything or everything you might imagine. Instead, you look at the tree and you figure out, from here I can imagine, and what can I imagine? And then you start tweaking it and pruning it and shifting it and moving it. And over time, you can get to anywhere that you might want to go, by discovering it and nurturing it. The question is, how do you learn that mindset? And the answer, of course, is incrementally. So let's look at it. The key idea is that people's minds don't change how they work. The way people's work changes your mind. In fact, if you look at the work around behavioral influencers, we can tell that there are a number of influencers that change your actual behavior. Number 6 in that is your desire, what you want to do. 5 things are ahead of that: your practices, your tools, your habits, your norms, peer pressure. All of those sorts of things have a far greater impact on your behavior. And interestingly, since the brain does this associative learning thing, the impact of what you do on what you think you want to do is stronger, it turns out, than the other way around. So if we just change our behavior, pretty soon we will find ourselves wanting to do different things with different desires and with different ways of thinking about the problem. So that's the key idea. We need to learn by doing. We want to guide the fingers to do the right thing, and then the brain will catch up. And then the brain will start to reinforce the right thing. So there are 3 common ways and 3 excellent ways to do this. All of them are incremental, and all of them are supported by an existing mender. And let's look at them. Mentorship on the job, katas worked on in a lab, and katas done on the job. So mentorship on the job. This is the most traditional way. It's the way that most people who are menders learned to be menders. And it's by an apprenticeship. It takes years. You start with someone who knows how to code and knows how to code well. And then over the course of multiple years, you start mentoring them in all the skills and techniques and mindsets. And they work with code and work with different code bases, typically at different companies, and slowly grow this ability. Now, also, each master craftsman can have a limited number of apprentices because it requires a lot of attention and awareness by that master craftsman to really understand exactly where the apprentice is at any given moment and help them find the next thing to learn. Over time, you develop really deep expertise. It might take 5 or 6 years, but you become an awesome mender. You become a master craftsman, and you can then start spreading it forward. Many great coaches are available who work in this style and can really help you become a true master at your craft. But it's slow, and it's very, very hard to scale. And because of that, or partly because of that, the industry has developed a new technique, and that is these dojos, katas, learning a kata that you can play with that's not on the job. You step away from the job work and you work on this problem. And these problems are in a lab. They are designed to introduce the pure essence of exactly one sort of thing that you would encounter in the world and give you the ability to very quickly and repeatedly engage with that essential problem. Whereas on the job, you'll run into that essential problem every so often. Some of these maybe every 2 weeks. Some of them it'll be every day. But slowly, incrementally, you'll get it and you'll work through it. In the lab, you can just do it over and over and over every 20, 30 minutes. Okay, let's engage right with the essence again. Now, the problem then guides your fingers to discover something. And each of these problems being a very essential one will lead to you learning a couple of key behaviors. And everyone who does that will explore a wide set of behaviors and find this doesn't work, that doesn't work, this doesn't work, this one does, right? And they'll find the same couple of things that do. And so your fingers discover those techniques. And when they discover those techniques, you start reinforcing and practicing those. You bring those back to the job. You gain more nuance every time that you do the practice. And this becomes a way to learn that doesn't require the master to be present. Now, many masters at this point will use these in engagements where they will come in and get somebody started and then give some uh, selected set of katas for the group to practice. And the group will practice those katas over and over and over and over. And then the mender will come back a few weeks later and do the next step. Right? There's less nuance learning this way. And it's outside the job, so it requires extra time and effort for the learner, but it's fast learning and it's independent. And here's the third technique. The third technique is katas that you perform on the job. Now, it's sort of a blend of the other two. And it's interesting because on the job, you can't create the problem. And the problem is really what is guiding the learning in those katas. So instead, what we do here is these katas tell you exactly the behavior that you're looking for. And most importantly, they tell you how to see the problem in your regular code. All of these katas, being the essence of a legacy problem, they show up in your code. Right? And so by guiding carefully and very specifically the learner, you can find out where this problem really exists in your code. And then when you see it, you can play with the behavior. Right? These give very fast results because they allow you to see those problems that you were encountering once a week. You were actually encountering it 5 times a day, but you only noticed it once a week. Right? And so you get many more times to practice. You practice it deeply on your code. You do one behavior at a time. However, it does slow productivity because you're doing this on the job and you're doing very intentional learning. Intentional learning is slower than just performance, right? And so you'll see a decrease in productivity. And you can only do this for prefab skills. The regular katas being a problem, you will discover a set of skills and each one is generative. With these ones, because they help you find a problem and help you see what to do, they really are for prefab. Someone needs to go identify each skill that needs to get learned and show you how to see it. Now, Deep Roots, my company, provides workshops that work in this way. As far as I'm aware, we're the only ones that provide things in this way, but we actively hope to change that. We believe that this is the most scalable and effective way to create menders, and the world needs a heck of a lot more menders. So we're trying to get a lot more people out there able to help people learn in this way and generate a wider set of skills. Now, at its heart, all 3 approaches are trying to teach you to internalize something like this, right? This is the insight loop. This is the way that I think about it. But all of the menders that I know have some similar cycle that they're going through. And the key to mending is to go through the cycle faster and faster and faster. Right? Menders don't try and do good. They try and do slightly less terrible. So we want to get a smaller degree of slightly every time that we practice so that we can do this loop more and more and more quickly. We want it just barely less terrible. Right? And you see at the bottom right of this, safe, better, no worse, that's the ratchet. Whatever you're doing, every loop that a mender uses has a ratchet for their particular kind of work. Some way that we're ensuring the change that we're going to make is better and no worse. Right? And it's the small incremental change. The write it down and safe step, that's where we're doing that tiny, very safe change. So those 2 elements, the safe change and the ratchet, are at the heart of this loop. And this loop is how menders approach all their problems. This is, as clearly as I can articulate it, the essence of incrementalism. Of course, the devil's in the details. It really takes intentional focus in order to develop that mindset. When people start, they're able to do that insight loop every couple of hours or maybe every 3 minutes. When people have achieved mastery, they're doing it every minute or 2. Sorry, what I meant when they start, they could do every 30 minutes. Yeah. When they have achieved mastery, it's every minute or 2, sometimes even faster. Just click, 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 click. And to get there requires learning a ton of little techniques. The thing that slows you down is friction of varying sorts. And so you find that friction and you fix it. And you find it and you fix it. And those are investments that you're making in yourself, in your team, in your process. Right? So when you do the workshop with us, for example, you expect that there's about a 40% initial productivity drop. And then these things pay off quickly. Each shift you learn, it only takes a couple of days and it starts having a return. But you do have that initial drop. And then while the first one's giving you a return, you're trying another one, which is going to drop you. And so you are still making investments during that time period. Now, it's not as bad as what I like to say. What I like to say is it's a 40% slowdown for 6 weeks. It's actually not quite that bad because a lot of those things start paying off early. But that's a good way to talk about it with managers and product owners because they can sign up for that and make that investment. And then when it's better, everyone's happy. Right? And as a reward for doing that investment, just learning and internalizing that insight loop that I talked about will typically cut the completion time for each story by about half. So you get about twice as many stories done in the same amount of time, and you will produce about 30% fewer bugs. There are a whole bunch of additional techniques, more advanced techniques that will continue to drop those bug rates down until eventually you get to no bugs. And that is where you want to get. But in that first 6 weeks, you can drop your defect rate by 30%. So let's talk about how to get there. And the problem is we're in a culture that makes it very hard to adopt that. Our feature factory, companies are barely holding on. They feel like they're just right at the edge. And that's because of all the technical debt, all the risk and things that it's creating make it so that they're always worried about whether they can get the next feature out. And the next feature is going to be required in order to keep the customers or to expand the set of customers. So there's no real time for continuous improvement. They need to go fast right now. And what we need to do is incrementally find a small space for us to make a little improvement and then leverage that to go better and better and better. Okay. There are two key leverage points to start small and grow and grow and grow. And those are bugs and demos. Those are the places that companies tend to be open to change. Right? So let's explore how we would use each of those to start making a change. First, demos. Now, in a demo, the way that we traditionally do demos reinforces the feature factory. We show the feature, we show the product. Instead, I propose to do a slightly different demo. In what you want to show is two measures and an example: a value measure, a progress measure, and an example. So if I'm working on something, I want to show one very concrete example of having done it. If I'm, say, trying to change the way that we do data access, I'll show, here's the way that we used to do data access. Here's the new one. We switched from that library to this one. It's tidier in this way. And because of that, these couple of risks and bugs that were there aren't there in the new one. These couple of manual steps we had to do now are automatic. Life is a little better. Everyone gets a really concrete example and sees what it is. Right? And then we show the progress measure. We say, and here are the 13,000 places that our code does data access. Right? We know what they are. We found them by analyzing the code. So we just need to change all 13,000 of them. Right? But we could do that over time. And then you show a value. You say, given the number that are there and the risks that it causes and so on, this is what it's costing the business every year in terms of lost opportunities, in terms of dollar, in terms of risk. Right? And so now here's the money that we could choose to invest. Here's the size of investment that we will make over time. Let's go after it incrementally. And now we don't need to fund that as one big project. We can say over time, we're going to do 10% of our time driving this down, and we will see progress along the way, and we should see value accrue. And as that value accrues, we will put that time back into this project. The other place that groups are vulnerable to change or open to change is with bugs. And for that, I propose safeguarding. Safeguarding is a technique. It's built on doing a 5 whys sort of a root cause analysis, but it presumes there isn't a single root cause. Instead, there are many, many contributing factors, and every defect is different. And so what you do is every week you just sample, you pick a defect or two, you look at what the causes are for that one, you do a small change that improves it, you execute on that, and you demo it. And you show that I did a little bit of investment and I slightly reduced the risk, things are a little safer. And over time, you show that the bugs are starting to drop. And so you allocate a certain budget that will be spent every week for whatever shows up. And that budget then naturally goes towards whatever bugs are actually present, and thus to whatever causes are actually causing bugs. Right? Over time, that will guide you with both the ratchet and the incremental change. So both of these have the same sort of ratchet and incremental change. Right? You've got data at a demo that's the ratchet moving you forward. You've got data in your defects, the defect themselves that are guiding towards what investments are good to make. Right? Those are your ratchets. And you're making one small improvement at a time of the kind that is safe to fail, that is small enough that it's okay if it doesn't work. So with that, we have now addressed how menders incrementally solve the four most fundamental problems: dangerous code, bugs, untestable code, how you make more menders and get enough people that have those skill set, and how you get permission to actually mend code. Okay? And the root of it is we don't try and do anything good ever. We just try and make it slightly less terrible. For each problem, you need to find your ratchet and your safe change. You want to make safe changes you can afford today. You want a ratchet that can guide thousands and thousands of those changes done by hundreds and hundreds of people and always know which way is forward. Once you have that, you do it again and again and again. So the place I recommend you start is by start making names slightly less terrible. I have a blog series you can read. The URL is there. Articles on naming as a process. Read that. And don't just read the whole blog end to end. Pick one piece and try and put it in practice. Find a name that is misleading and make it non-misleading. Find a name that is slightly dishonest, make it a little more honest. Introduce the honest naming template, right? Just make one small change to one name, and it will be hard. And then do it again, and it will be slightly less hard. And over time, you will make your names slightly less terrible, and you will learn how to make names slightly less terrible. You will be on your path to learning to become a mender, and you will be mending the number one cause of bugs for your team. So thank you very much. I hope that people start putting this stuff into practice. I want to see a lot more menders out there. And if there are any questions, I'd be happy to answer them.
Thank you very much, Arlo. That was awesome. You cannot hear the claps, but I'm sure people are clapping behind their keyboards now. So, and yes, if you do want to join us on the path of mending, I share with you the Legacy Code Rocks community, so you will find a couple of other folks here too. And yeah, I can just recommend everything Arlo said. I like how practical it was. As everything you share, it's always concrete, always great examples. Okay, we have a few minutes. I will take the questions that are starting to pop up. And the first one is, does technical debt cause bugs, or is it craft that slows down the future progress, according to you?
Okay. Technical debt, in my mind, is a hugely overloaded term that means a bunch of different things and isn't the right way to think about it. The way I think about it is there is damaged code, unhealthy code, dangerous code, right? For whatever reason, this code is causing problems. Now, the most common problem that it causes, the most impactful one, is bugs, but it also slows down development. And often the way it slows down development is because we can't afford too many bugs. And so we all slow down and become far more careful. And that does decrease the number of bugs by some. But we still end up creating more bugs than we would if the code was safe to change in the first place. Right? So I'd like to get out of the generality of talking about technical debt and using the metaphor, and instead talk about dangerous code. It hurts. That's what we're trying to fix.
Yeah, I agree. And there is actually a follow-up question on that. What do you think about talking about technical investment when you want to bring that shift in the culture of the company and you want to convince other people, other stakeholders, and instead of talking about debt, maybe talking about investment in that improvement?
Yeah, that can work fairly well. I personally end up nuancing it a little bit and talking about both investment and repair. And what I talk about is that we all want to make investments that will have a rate of return and make new things possible. And that's where we're going. We would love to do that. However, where we're at right now is we've just got so much damage and pain here that we can't even keep things going as they are. We're drowning, right? So first we want to solve that problem so that we have a little bit of space. And that gives us the seed capital that we can start using to make investments. And if you look at DevOps is all about making those investments. It assumes you've already got seed capital. It assumes you've already eliminated all the painful code, right? So if you want to start your DevOps journey, first, you have to fix all of this dangerous and painful code. After you've done that, which takes a couple of years, then by all means make all these technical investments, and the whole DevOps initiative shows you how.
Yeah, and from my experience, I agree with what you said, that the showing concrete examples and data and talking numbers and going beyond just the technical jargon, but really going to see what is the impact on the business. It really talks to all the people, all the folks in the company who are not really technical. They don't really understand the difference. They cannot really see the code, but they do understand like the bugs you are showing up, the cost to the company. And so using that in the demo to that will really back up the arguments of that improvement and these repairs. All
Yeah.
right, I think no, there is no new question.
Mm-hmm.
So thank you very much, Arlo. Um, you mentioned, yeah, I think you're doing some classes, right? You can do some mentoring for people who want to go further.
Yes. So yeah, for people who want to go further, reach out. We have the workshop, the fundamentals, foundational workshop in code by refactoring. And there was a URL in the middle of this somewhere.
Yeah, we will share the. I
We'll go
will
ahead
put
and
the
share it.
URL in the
Yep.
video.
Um, yeah, all of our stuff right now, we are deeply focused on teams and companies. So if you are an individual and wants to do this, reach out to me absolutely, and I will help. I'm happy to help and guide. And I'm going to try and help you make some progress in yourself, and also in getting your whole company to see the value and to be able to start making these investments. We really want to help these first excited people become the champions and around their company. And we do train the trainer so that those people then go out and spread.
That's awesome. Thank you very much, Arlo. And we're going to take a 10 minutes break and we will be back with Jessica Kerr, who is here in the audience. I saw her. And we will have a nice roundtable discussion on legacy code.